Okay, we are recording now. Um, so to start, I just wanted to let me share my screen here and go full screen on this. So to start, I just wanted to go through a little bit of course business. So this is the schedule of what's remaining in the course. So we have eight eight lectures left, or 8 class days left. Today we're going to talk about hadrons and partonization, and then we're going to go on to talk about QCD. So one thing that I find is this topic of hadronization and partonization, that Griffiths actually has a really pretty clean explanation of this in his particle physics book. So I am suggesting as the reading for these topics that you look at Griffiths chapters 8 and 9. You can also look in the Halzen and Martin text as well, but I find Griffiths' description is a little bit more straightforward on this topic and easier to follow. If you don't have your Griffiths texts, I posted these 2 chapters digitally into the information section on the course Blackboard. So you can look at them there. So please verify if you get a chance. Make sure you can access those. I know myself, I didn't remember to bring home my Griffiths book, and I think we had it in the the graduate office for you guys. So I posted that for you, so you should be able to get your hands on it. So we're gonna try to wrap up this discussion about hadrons and partonization today. And then next lecture and on Thursday and on next Tuesday, we're going to try to talk about QCD, what the Feynman rules are for colored objects interacting with one another, and what kind of interesting physics that leads to. And then the following 2 weeks, we're going to talk about weak interactions. And then on the 30th, I have watched Particle Fever. So I don't know has anyone seen this movie? Jonathan, have you seen it? So I thought I saw you nodding your head. Yes, like you had seen it. So this is a really nice documentary about the discovery of the Higgs boson, but it kind of gives you a nice overview and kind of the internals of how a large international particle experiment works. So it shows you some of the political churnings and turnings, and something about the machinery. So we're going to watch that documentary. You'll see part of your homework assignment that I posted. The 7th homework assignment is to answer some questions about this video. So we're going to watch that on the 30th, and then that'll kind of set the stage. They're going to talk about that they discovered this thing, and then the lecture after that will talk about the Higgs mechanism and how we think particles get their mass in the standard model. And then our last day of class is the 7th, and that's when we're going to do our student presentations. And I'm going to say more about that on the next slide. Sorry, I'm going to pause for 1 second and see if Brian's in the waiting room. I just noticed I couldn't see that anymore. He is. There's Brian. Hi, Brian. Can you hear us?
Yeah, finally, yeah.
Okay, great. Thanks. So we're just going through some information. We just went over the schedule. I'll post these slides so you can see it, but we were just getting into what assignments are coming due. So the midterm is due today. You missed it, Brian, but we just realized that the assignment for the midterm in Blackboard wasn't showing up as available to you guys, but that's available now. So when you have your solutions, you can post it on the associated Blackboard assignment. It's set that those are due by end of the day today. So at 11:59, I think that will close. So everybody try to deposit their midterms by that time. If there's some technical issue you're having, send me a note and I can, extend it for an hour or something to help you get it in. or send me an email with a copy of it, and we can get it submitted to Blackboard the next day just to show me you have it done. So homework 6 we had due on the 17th, I believe, which is this Friday. Have people started homework 6? Does that still seem like a reasonable deadline? Or do you want that pushed back a little bit? I know that's...
I sadly haven't started that.
I have started it. I don't remember how far I've gotten. I've
Yeah,
spent the last 5 days doing
I'm
thesis
thinking that
more
might
than
make
that.
sense since we extended the midterm date to push that back to be due on Tuesday, so you guys have the weekend to work on that at least, and we can see how things are doing. So I'll do that. We'll push that back to be due this next Tuesday, a week from today. So that would be the 21st, I think. Yeah. So we'll make it due the 21st of April, and I'll change that after class here. And then I posted chapter 7 homework 7 yesterday, and again, it has on there that I would like you guys to read chapters 8 and 9 from the Griffiths textbook, and those are posted on the information section on the course catalog. If you're having trouble getting a hold of those, let me know, and we'll make sure everyone can read those. These are the chapters about QCD from that text. And that's the last homework that I'm going to consider as a required assignment for this semester. That's I forget what the due date is, but it's essentially the last Thursday. So I think I must have made the due date like May 7th or something like this for that assignment. And then the other things that are still out there is some extra credit opportunities. Just to remind you guys that I have the sheet posted for you guys to do a little write-up on a physics seminar that is about particle physics and answer some of the questions to get some extra credit towards the course. I'll probably also, in that same vein, post a homework assignment about the weak interaction material that we're going to cover, and just count that as extra credit to help people along here. I'm trying in this weird situation to be very generous with the grades this semester, since it's all a little strange and no one asked to be in this scenario. So we're going to make this weak interaction assignment is normally the final assignment, but I think I'm going to just make it extra credit this semester so that everybody can work along on that. The other thing I'm changing or adding is that if you want, and I'm going to say something a little bit more about that, if you would like to attend some of the American Physical Society talks that are going to be starting on Friday through Tuesday, I believe, and you want to use that as one of the presentations that you're going to watch instead of one of our WSU seminars, I will accept those as extra credit assignment as well. So let me just jump out of this real quick and show you that. So just as if people aren't aware, I mentioned this in the physics chat this week, but the APS meeting has moved to be a completely virtual meeting. So people can get online and register for it. It's open and free to register. You have to just go to the aprilaps.org. I'll post the link on the Slack channel and on the announcements after class. And you can sign up for this. And this is an interesting meeting for this course because this is the American Physical Society meeting where they focus on particle physics, high energy particle physics, and particle interactions in nuclear physics. So people can, you can find the schedule here. It starts on Saturday and runs through Tuesday. You can find the sort of plenary program, sort of the main topics that are going to be covered. So if there's something that catches your eye and you want to watch an interesting APS talk, I would encourage you to do that, and I'll be happy to have you write that up as extra credit if you attend one of those, just as another option. Okay. And the last bit I wanted to mention, because I think maybe we haven't talked about it too much, is what we're going to do for the final. Um, so I think the way I want to handle the final this semester in this situation is just focus on the student presentations and written reports. And I'm not planning to give you guys a written calculations based part of the final this semester. Um, I'm going to talk a little bit about how I want to kind of hide that into this bit here. So we will have final student presentations and a written report. There's an oral component and a written component. The oral component I'm going to take is 30% of your, right? So the final exam is supposed to be worth 50% of your grade. That's what we said in the syllabus. So 30% of your final course grade is going to come from this oral component. And right, what do I want you to talk about in these final presentations? The talks are supposed to focus on a modern or seminal experimental or theoretical result. And we can have a conversation about what that is. Maybe we need to, I would like you guys to think about over the next week what topic you'd like to cover. And if you know what that is, let me know and I'll post it so everyone in the class knows what it is so we don't have a duplication. If you don't know exactly what it is, you can send me a note. I'm happy to make a suggestion to you as well. What something interesting to cover might be. But if you had something in mind, some experiment or some interesting bit of physics that you've focused on, then go ahead and include that. The talks are going to be 20 minutes long, and then we'll leave 5 minutes for question. This just divides up the time naturally for the meeting. So we'll basically break it into 3 25-minute slots so that everybody can have time, that final meeting, class meeting time, to go through this. I'm planning on sending invites to the rest of your colleagues in the physics department if they want to come watch that. They can also ask questions. So we'll invite them to join the Zoom session that day as well, so they can hear what you guys have researched. It should present enough background material to understand the result that's being presented. And right, the sources that I want you to draw from, like we focused on earlier in the semester, are from interesting peer-reviewed physics journals. Okay, so focus on high-quality journals to get your information from. The written component, I want a 5 to 10 page write-up. That again, I'm going to use this basically as the written final, and I'm going to count this as 20% of your final grade, and I'll collect that on May 14th. Again, it should describe the details of your chosen topic. I would like you to reference and cite at least 3 peer-reviewed sources in the document. So, by the way, textbooks are peer-reviewed, so that counts. If there's some textbook that you find is really interesting, those are heavily reviewed before they typically go into publication, and cite them appropriately. The thing I would like you to do, right, is to focus on either an experimental or theoretical result. But in either way, I would like there to be some section of the text emphasizing the comparison or agreement between the experimental results on the topic and the theory that's presented. So agreement between experiment and theory, and describe how the theoretical calculations, at least at some level, are done, and the experimental techniques and the uncertainties on each. And, one place where when you're describing the theory, try to describe it at the level that's appropriate for what we've discussed in class, right? So I want you, right, if you're trying to describe the theory, it should be showing me the Feynman diagram and showing me, how they, you don't have to go through the full derivation, but showing me that they calculate an invariant amplitude to get a cross section, or something at the level that we've been talking about in this course. Okay. And if you can kind of go through and point out the key points of the theory, right? Here's the propagator term they're using. Here's the assumptions about the vertex, the coupling between this and that. That sort of thing. I would like you to kind of explain it in the field theory language, right? The Feynman rules language that we've been talking about this semester. I'm going to send a Blackboard announcement around in the next couple of days, and I'll write all these. I'll write out a little bit more detailed prose, so this is all clear. But I just wanted to set the stage today. Okay, and that's going to be it for the semester. Are there any questions about that off the top here? Is it all pretty clear? Okay.
Yeah, if I wanted to find your seminar that you gave.
Sorry, Brian, you were cutting up a little bit. Can you say it again?
The seminar that you gave at WSU about neutrino mixing.
Yeah.
Is that on the internet somewhere?
I do believe that that's posted. So all of the seminars, let's check what's there right now together. If you go to the physics webpage, I'll post the link to this if we find it. So if you go to the physics webpage, there's a drop-down section for the seminar, spring 2020. So let's see what's there. So mine is not there. I can post mine, I've got my slides for that, so I can post it. Dr. Meyer should have the audio recording of this. These latest two that were done Zoom-based, the YouTube links are available for those. So Ian Lewis talked about Higgs boson physics at the Large Hadron Collider, and Kirsten talked about probably this one is not at the level that we are, not the topic that's relevant to this course, but this one by Ian is probably relevant. So yeah, probably this semester, looking at this, it's probably like, I guess we could use this one, talking about dark matter and dark matter candidates and that sort of thing. Mine and Ian Lewis's are probably the seminars that are relevant to this course that I see this semester. Which there's not a lot of them. That's why I also said that we could use the APS seminars as well. I'm hoping that the APS seminars get recorded so that we can look at them later, but I haven't heard for sure if that's happening, and I'll let you know if that's the case. But there are at least a few choices here, so you should be able to complete the extra credit if you want to from what's here. I'll just post my slides on this on the channel so people can find them. Okay. Good. All right, so I'm going to stop sharing here. And okay, are you seeing my iPad screen now?
Yes.
Okay, great. Oh, sorry, I'm muted. I'm talking to myself here. So we ended last class, we were talking about how to characterize scattering off of bound extended objects like a proton. And we said that we could try to characterize that scattering in terms of these form factors, right? Basically kind of hide our ignorance about what's going on in these form factor terms and just find them experimentally. And right, so we were thinking about bringing in, high energy probes like an electron and scattering them off of some bound nuclear state like a proton, some nucleon, or maybe a bound nuclear state like some gold nucleus or something like this. And right, we would basically just scatter off of this with a photon here. And we said this is nice, right? We can basically try to treat this like we did our other processes. We can say there's some kind of current term up here that takes into account the initial and final states and the coupling of the electron to the photon. And the nice thing is this side of this diagram is purely electromagnetical, so we can use the QED rules that we described before to calculate that side of this diagram. And then the other side, we could generalize that we have some bound spinor state that's going to scatter into some final state if it remains a bound particle. And we said that we could, right, basically use this photon that we're scattering off of the proton as a probe to look at the structure of this bound object, right? And we saw that we could measure this form factor that's a function of the momentum transfer of the photon. And if we turned that momentum transfer really, like if we turn that really low, right, we had a low energy photon here, we basically got something that told us about the physical size, the physical extent of the object that we're scattering off of. And as we turn that up, it tells us more and more, right? It's basically like a microscope, right? As we have higher and higher energy photons, we can resolve smaller and smaller pieces of the proton, right? So that's kind of what we were talking about when there's this Fourier transform. And so there's an inverse relationship between the energy of that electron and the spatial scale that we're probing the composite object with. But so it's interesting to keep turning and turning up the energy of that exchanged photon, because I can look at finer and finer detail into that composite object. But at some point, right, an interesting thing happens, and as I turn up the energy of that photon, I'll start to probe smaller scales, and that photon will no longer be interacting with sort of the composite object that we call the proton, but it'll have such high energy that it'll just be interacting, right? The scales that it's observing will just see individual quarks, and it'll start scattering, having hard scatterings with individual quarks. Right, we know what can happen then is if we have enough energy is that photon that's being exchanged with the proton side, it can transfer almost all of its momentum to a single quark inside of the proton, right? So you can imagine as my energy is turning up, my photon can start seeing smaller and smaller scales, and eventually it has enough energy that it's just going to transfer a huge amount of energy to a single quark inside of the proton, and then it's going to try to blow that quark out of the, right? It's like I have these set of quarks inside of the proton, and it can try to pull that quark out of the proton. And that's when we lead to this idea of hadronization. If I hit the quark with enough energy, it's going to try to escape the proton. We've talked about this a few times before, this kind of picture that it's a strongly interacting particle, and so it's going to stretch this gluon behind it as it tries to escape the proton. And if there's enough energy in that gluon field, it can produce other massive particles, and I can eject, say, a pion or some energetic hadron from out of the proton material. So as Q, right, if Q is, much, much bigger than 0, if I have large momentum transfer to the proton system, suddenly what I get is that the proton in the final state is no longer a single object, but it's a bunch of different particles escaping here, right? So maybe I get the proton coming out, but maybe I get a pion or particle N1 and N2, right? I get a whole bunch of different particles escaping because suddenly I pull a quark out, there's a bunch of energy in this gluon field that can turn itself into massive particles. Okay. So this thing that was a nice clean process that we saw before is suddenly this messy thing where I have something that's like an electron interacting with a proton, EP scattering, but then I end up with something on the other side that's like EP plus, particle N1, particle N2, on and on and on. I can end up with some mess of particles on the final side. Okay, so how do we characterize interactions like this? Well, there's a couple things we can do. one thing is we can try to characterize this, right? What were we doing? We were talking about the initial momentum and the final momentum of the electron. We could characterize this interaction like this, and that tells us about the momentum transfer, right? If we measure the electron side and how that changes, that tell us about the 4 momentum transfer to the proton side, right? Because the Q is shared between, the Q from the photon is shared between these two sides. And then the proton also had some, say, some initial energy, some 4 momentum that we could call, I don't know, P, momentum P. But what are we going to do for the right-hand side of this? Now I have a bunch of particles with a bunch of different energy and momentum, right? One thing we can do is collect all these up and measure what we call W, which is the total invariant mass of this side of this interaction. Total invariant mass. So what does this mean? Remember what the invariant mass is. The invariant mass is just, what is the invariant mass? Do you guys remember what this means?
It's not the rest frame mass.
Is it p squared minus m squared or whatever?
I mean, it essentially ends up being the rest mass of a particle, right? It's sort of the, it's the mass, right? It's the true mass of the particle that you would measure independent of frame of reference, right? And so we had a prescription for that, right? Like, for instance, we can measure the invariant mass of, say, if I have a pion, it decays into 2 particles, I could find their momentum and I could take a special combination of those 4 vectors, right? I could take the dot product of those 2 vectors and I end up with an invariant quantity that we calculated this out in class, just ended up giving me the rest mass of the initial particle that generated those 2 things, right? But what it told me, remember, was it told me, right, if I had 2 particles and I calculate an invariant mass, it somehow tells me not about the mass of those individual particles, but the particle that might have created those 2 things, right? Something like that, the total rest energy in those 2 particles. Right, so it's a little bit different than a rest mass, right? So that's why it's different. Like I could create, for instance, a real photon that could carry some energy and it would have 4 momentum with another particle, right? Like I could have a pi0 decay into 2 photons. They have 0 rest mass each, but they have some 4 momentum that when I do this, right, when I take the scalar product of the 2 4 momentums of those 2 photons, I would get an invariant mass from that, and that would tell me about the mass of the pi0 that they started from. Okay. So I could play that same game here, right? I could basically just find all of the 4 momentums of all these outgoing particles, and I could do something, right? Now it's a little bit more complicated than just having 2 4 momentums, but I could basically create a scalar quantity out of all these 4 vectors and sum up right, I could take like 2 of these and make a 4 vector and get an invariant mass and do that for all different combinations of these particles and find a total invariant mass for this side. And it should basically come out to tell me about the particle, right? Something like the particle, the mass of the particle that generated this spray of particles out on the other side, right? So if I do this right, I should get something that's like the mass of the proton, unless there are some stable states that were generated, right? So, right, if the proton really just created all this spray of particles on the right-hand side, I would find that the total invariant mass is always just the mass of the proton. But what I'll find is that it's right, some other things can happen, like that photon that hits the proton can excite the proton structure into some delta that can then decay back down and give off a photon, and I can end up finding other resonance states of that proton sitting there. And we'll see what this looks like in data here in a second. I'll show you some pictures of this. Okay, so it's a messy picture, but we can make some progress here. And how do we do this? Well, we want to try to, again, measure some cross-section, some differential cross-section. And what we did before is, right, we calculated, right, these, say, this L term for, say, an electron scattering off of a proton, right? We calculated these things and we wrote this down in terms of the form factor, right? So these are just the 2 currents here, that tell me about the interaction here. Now this is no longer the right thing to do because we don't really have, for the proton side, we don't have necessarily a current like we've defined before, because now we're splitting up into a bunch of different particles. But we can still try to write something very generic. Usually it's expressed as W, and this is going to be some tensor quantity that captures the nature of the particles, the four momentums of the particles and their interactions on the other side. So we're not thinking about this like a charge current anymore because I'm breaking into lots of different particles, but I'm trying to just generalize this into some tensor form that looks like what we've written down before that can explain some of this scattering. And your book goes through some of the details of this, but in the end, it turns out that there's a pretty simple form for what this looks like. This tensor has to be related to the physical quantities that I have in the problem. It has to be related to, the momentum transferred from the electron side into the system. It has to be related to, say, the coupling of the electron to that cube or to that photon. It has to be related to the mass of, say, the proton. That's something we have in this problem, the momentum of the proton. And it turns out that there are just a few ways with the quantities that we have available to us in this problem that we can generalize this, and it ends up looking something like this. W1 Q nu over Q squared plus W2 excuse me, 1 over m squared P mu minus P dot Q over Q squared. Okay. So it turns out there's only so many independent ways that you can express that with the 4 vectors that are available in the problem, right? Really, the only 4 vectors we have in the problem are the independent 4 vectors are that momentum that's transferred to the proton side, right? And the momentum of the incoming proton. Here's something m that's like the mass of the proton here. And here's our G value that we've seen several times before that tells us something about the coupling of the G side. So we have some of these that look like, right, all of these are tensor quantities, but they're different ways to make the tensor property that we're interested in specific here. And these guys, W1 and W2, what are these things? These things are similar to those form factors we saw before. Okay, these are called structure functions. And they're basically functions of Q squared that tell me about the scattering, right, how this cross-section proceeds. So this is a really crude way to break this up, but it's basically saying, okay, I don't, right, so it's the same game except for now, right, instead of scattering into some final P state, I say I can scatter into lots of different final state particles, and I'm just going to characterize this in terms of the total invariant mass of this object. And I'm just going to hide all my ignorance in terms of these 2 structure functions. And I'm going to go measure these, make a bunch of different physical measurements of this cross section and determine W1 and W2 as a function of my kinematic properties from experiment. Okay, so this does not tell you about, right, the structure of all, right, it tells you something about how the invariant mass, like the function of the invariant mass that gets created as I increase Q, but this doesn't tell me about the nature of QCD. It's just going to tell me sort of some of the underlying properties about the compositeness of the quark. It tells me how the invariant mass, like what distribution of invariant masses the quark can hadronize into, like how that gets broken up into these different coupling terms here. And that's something we can go measure experimentally. Okay, so that's great. So the whole takeaway here is we at least have some way of tying a cross section to something about theory, right? So this is not QCD, but what we should be thinking about is whatever underlying theory that we're going to try to write down when we describe QCD, right? We're going to try to write down interaction, right? How a proton, a bound state that we call a proton, is formed from these different quarks, right? These different subatomic particles that are going to make up the compositeness of the proton. That theory had better be able to predict the proper structure functions that we measure from this generalization, okay? So this is sort of just like a way to characterize how much of, right, the hadronization, right, couples in these different ways to the system. That doesn't tell us about the rules of QCD, but QCD, going the other way, had better predict these relationships properly if we understand QCD. Okay. And historically, these were all done before we knew QCD, right? And this is part of the story of how we ended up developing QCD, right? We had some measurement of form factors that let us know that the proton had extended size and shape and the charges were distributed in there. We saw that the proton was breaking up when we increased the scattering, right, the momentum transfer to the proton side to a large level, and we could start measuring these structure functions to characterize how the proton was blowing apart. And then people could start writing down guesses for how, like, what are these objects that make up the proton and how do they couple together? And then they had nice checks to go up against to say, can I predict the measured structure functions from my QCD theory? Okay. So whatever theory we develop for proton constituents has to be able to generate the observed structure functions, the observed form factors, all of these sort of generalizations that we were making. Okay. So if we have precise experimental measurements about the structure function and the form factors, that's great because people that write down a theory for QCD can test to see if they get those experimental values back out. What else can we do? How else can we understand the constituent particles inside, say, a proton or neutron? Okay. Well,
we could do it by looking at decays, right?
We could do it by looking at decays? How? Like, what do you mean?
Well, we could, I guess that, I don't know.
Shoot high energy particles at them.
At what? At the proton?
Yeah.
So that's what this first method is, right? The last two ones we're talking about, that's the idea, right? Take a proton, right? That's the really general thing. These structure functions and these form factors that we're talking about are exactly what you measure if you take high energy particles, high energy electrons, and you shoot them at protons, right? You can either, right, have the electron just bounce out and say something about the bound structure of the proton, or you can transfer enough energy over to the proton to blow it to bits and then try to characterize the bits that you see, right? That's sort of the layman's way to say what we've been talking about the last 2 days. I can turn, so the answer is I can turn this around and go the other way. I could say, what if I could generate the constituent particles and let them create hadronic material after an interaction? Okay. How can I do that? Do we know a way to do that? Well, here's a way we can do it. We can take an electron and we can take a positron. So I imagine I could, right? So this is, we can make a linear collider, say. And I could have a source of electrons. You could imagine stripping electrons off of an atom. There are also ways to generate controlled beams of positrons. Okay, so imagine I just have those sources of electrons and positrons. I could bring them together. What's going to happen when I bring an electron and a positron together?
They're going to
Pure energy.
annihilate.
I get energy, right? I get a photon, right? I get an electromagnetic annihilation here, right? I get an annihilation process like we see in QED, sorry. And now, what can happen in this final state? Well, we know that it can decay into, say, other electrons and positrons. It could decay into a muon and an anti-muon. It could decay into a tau or an anti-tau. But quarks are also charged. The constituent particles that make up the proton, because we see that they have some charge distribution inside of the proton, they better be charged themselves. And if they're charged, they better couple to the electromagnetic field. Okay? And so whatever these constituent particles are that we call quarks now that we have more idea, we can generate them here, right? So I have a quark and an anti-quark can appear out of this process here. So I can create from the photon energy that I can produce from E plus E minus annihilation, I can produce quarks. Okay. And what happens with these quarks? Well, these quarks, right, will try to fly off into my detector, something like that. But the quarks are colored objects, right? So we're going to talk about in QCD that they have this thing called color charge. And what happens is they like to try to grab onto each other very strongly by exchanging gluons with one another. And so now this process looks a lot like that process that we were talking about, pulling a quark out of a proton, right? I've created a quark-anti-quark pair real close together. As soon as they're created, the strong force is so strong that they grab each other very quickly with gluons, but because they have a lot of momentum, they'll stretch out that gluon field, and eventually that gluon field will snap, and I'll get, right, will not snap, will create more quark-anti-quark pairs, and I'll end up getting a bunch of regular hadrons out here, right? I'll end up getting, say, particle N1, particle N2, maybe they're pions, maybe they're protons. I get stuff flying out here. So this is another way of looking at that same kind of thing, except for now, instead of having the sort of messy proton, right, the messy proton, right, organization or a nucleus, this is really clean because I can just generate a quark and an anti-quark from the energy field produced by the annihilation and see how it hadronizes. So we call this hadronization. This is the creation of ordinary hadrons from the quark-anti-quark pairs that try to, right, that can't quite get free. And so they pull this gluon string behind them until the gluon string has enough energy in it to create massive particle-antiparticle pairs, and it can split into ordinary bound state hadrons. Okay, and well, this bit here, right? So by the way, what does this look like in a detector? We're going to see pictures of this here in a second. When are we done? Are we done at 1:15?
1:45, isn't it?
1:45. Okay, good. I don't know why I can never keep that right in my head. Okay, good. So what are we going to see in this final hadronization state? Well, it turns out that, right, since you have these two quarks that are produced from this energy field, they better have initial momentum that sort of, right, like points large momentum, and the total momentum of the quark and the anti-quark better follow the momentum that incoming virtual photon had. And so their momentums will point in two separate directions. And so what you end up with is a collection of hadrons that head off in one direction and a collection of hadrons that sort of spray off in another direction. And we call these things jets experimentally. So maybe you've heard this term jets when you hear about in some of the seminars here. So this is just a bunch of particles that come from the creation of a quark and an anti-quark pair, and because they're bound by a gluon, they create a spray of particles, but those spray of particles kind of all follow the initial momentum of the quark anti-quark pair. They kind of point one in the direction that the anti-quark was going and one in the direction roughly that the proton was going. Okay. And so if we saw something like that in our detector, well, that would be a really nice indication that there really are these fundamental particles that we call quark that have these weird properties, that they are really strongly bound, and that bound state energy increases as I try to pull them apart because suddenly they can create heavy particles as they fly out. And so if I could observe that in a detector, that I see a spray of regular hadrons that go out with very distinct back-to-back directions that point something like the initial, right, like the momentum, like the center of mass momentum of my initial electron and positron, that's really good evidence for quarks. Okay. And it turns out that I can look at this process. So before all this hadronization starts, I could just look at this side of this process, right? Without all the gluon stuff sitting there. I could just look at that piece of this diagram. And that piece of this diagram should not look too scary to you. That is just a quantum electrodynamic process, right? All I have there are 4 charged particles. I have an electron and a positron, and I have a quark and I have an anti-quark, right? And they're coupled to a photon. So that should be explained completely by the Feynman rules that we wrote down for ordinary, right, for QED. Right, what does it look like? I could write down for this bit here the invariant scattering amplitude. And what is it going to look like? Well, it's got to look something like, let me move this down. Got this a little close here. It's got to look something like this. It's got to look something like a V state. Let me write down the momentums of these things. So let's say this guy has 4 momentum that I'm going to call P2. This one I'm going to call P1. This one I'm going to call P3, and this one I'm going to call P4. So I can measure I'm going to label the 4 momentum of these processes, and here's the Q, the momentum transfer inside of the system. Okay. So I can basically just use my Feynman rules to construct what this invariant scattering amplitude looks like. It has to look something like this. Okay. So here's a bunch of the terms that I need for the states, right? These are the current terms I have in here. This is the current term that tells me about my electron side of this scattering. Here's my current term that tells me about the quark side of this scattering. Okay. And then, right, so that's those currents. So then I also need the propagator term. I have a photon propagator here, and so I can write down my photon propagator here. Well, it's going to look something like this. It's going to look something like P1 plus P2 squared. This is basically the Q squared term. And then I have something that's going to be my GE, right, that's related to the charge of these protons here. And then there's a big term here that I'm calling Q. What is this Q thing? This Q thing is just telling me about the charge of the quark. So this is the quark charge. Sorry. This is the charge of the electron squared. And this thing here has got to be something that's like the fractional charge on a quark. So remember our Feynman terms, there were terms in the coupling and the vertex coupling that cared about the charge. And so now on one side, I've got a fully charged electron, and the other side, I have a fractionally charged object. So this Q thing is basically just taking into account the fractional charge of the quark. And that's it. So the only difference here is I have this term that takes into account the fact that the quarks are fractionally charged here. And right? So I have an invariant scattering amplitude. So then what I could do is I could go and I could calculate a cross-section term, right? I would just square this thing. If I calculate a cross-section from this, it ends up having a form that looks something like this. Okay. Let me write this down and I'll tell you what these terms are. By the way, this is in the this expression I believe is also in the Griffiths text. Okay, so this is just a sort of nice factorization of what this cross section ends up looking like. So let's just point to some of the terms and what they end up looking like. I've got these M terms here. One of them is the mass of the electron. And one of them is something like the mass of the quark. Okay, sitting there, something like this. I've got the energy here. Okay, this is the total center of mass energy of the E plus E minus pairs initially. So I've got this initial energy for the E plus E minus system that's coming in here. So this is like the total available energy to the system. And I've got alpha, right? We know what alpha is. This is this term that's like the coupling, right? The electromagnetic coupling strength. I've got a third factor and I've got something that depends on Q squared. And we can make an approximation. Let's say we had that the energy, right? So one thing that's interesting here is that the mass of the quarks, right? Let's think about the mass of the quarks. The mass of the quarks can be different than the mass of the electrons. Okay? And in practice, we find that the mass of the quark is heavier than the mass of an electron. And so if I'm going to generate this process, well, there's also a kinematic constraint, right? If I want to generate those quarks, I have to have enough center of mass energy available to generate these heavy quark particles, right? I won't be able to generate those quarks if I don't have enough energy in my electron-positron pair. Right? If there's not enough energy to generate the mass, at least the mass I need, there's no chance of generating those quarks, much less with some momentum. And so I could think about setting up an experiment where, or I could think about this cross-section, and I just want to think about this. If I assume that I have energy that's larger than the mass of the quarks, which should, and let's assume that the quarks are heavier than the electrons in this system. Something like this. So the energy I have available is bigger than the mass of the quarks, and it's much, much bigger than the mass of, say, the leptons in my system. Well, if I make that assumption, then this whole expression, right, that I have written down above simplifies quite a bit. It just looks like pi thirds h bar q c alpha qc alpha over the available energy squared here, right? All these terms out to the right basically become, right, all these terms over here, you can see if E is very large compared to the other terms, these terms just go away, right? Essentially, kind of just become one. They don't go away, but they become one. Okay. And the next thing I can think about then is, right, so I can write down an expression for the cross section as I am turning up my energy here. And I have a guess for what this cross section might be, but this cross section will depend, right? Might depend something like sorry, right, is roughly independent of the mass of the quarks here. And here's an interesting experiment I could make here. I could make a ratio here. I'm going to define a quantity that I'm going to call R. And what this is going to be a ratio of cross sections. So I'm going to measure the ratio of E minus E plus goes to hadrons. And I'm going to compare that to E minus E plus goes to muons, mu minus mu plus, like this. Well, why is that interesting? Because this is interesting because in the limit where I have enough energy in this system that I don't have to worry about the mass effects of the quarks. This ratio, right, the only difference between those two cross sections can be the fractional charge coming on the quark, right? There's something about the fractional charge on the quark. And it turns out in this limit that this ratio, right, if I apply this limit, that this ratio just goes to the sum of the fractional quark charges. And then there's a factor of 3 that sits out in front. This is a weird factor that ends up being related to the amount of color, the distinct color charges that are available on the different quarks that are produced. And we'll come back to that when we talk about QCD. But essentially this just counts, right? This just sums over the fractional charge of all of the quarks that I have enough energy to produce, with a factor of 3 sitting out in front, which was something that was experimentally observed because there are actually 3 different types of quarks because they each come with color. So there's additional channels for those quarks to decay into, so it increases the cross section. Right, so imagine I make, right, so what does this mean I would expect? If I had, imagine I have enough energy in my beam so that I can produce ups, downs, and stranges. Remember that the mass increases as I increase quark generation. So I have enough energy in my beam that I can create up, down, or strange quarks in that process above, but I don't have enough energy, right? I'm below the energy that I need to create, say, charms or anything heavier than strange. What would I expect this ratio to be? This cross-section ratio? Well, it should just be 3 times that sum that I see here, the fractional charge on the quark squared, right? We know the up quarks are 2/3. I square that. The down quarks are -1/3 of a fundamental charge squared. And the strange quark is also -1/3 squared. If you calculate this ratio ends up being 2. So that means if I have, right, this is an interesting thing to go measure experimentally then. This means if I have enough energy in my beam and I've already measured, right, so I'm saying basically that I've already made a measurement of E minus E plus goes to muons because I can cleanly observe that in a detector. So I know that cross section. And now I'm just going to keep turning up the energy until I start making hadrons. And I'm going to always normalize everything to that hadron, to that cross section that I had going to muons. And what I should find is that, right, what I expect to find if I'm really making up, right, if my system is made up of objects that have this kind of charge on them, is that this ratio will be 2. And then if I, right, increase my beam energy, so now I'm going to turn up my energy on my beam until I'm able to produce charms. If I turn up my beam energy to where I'm able to produce charms, well, now what happens? Now I find that that ratio is going to increase because I'm going to add an extra 2/3 positively charged particle available to my system. And it turns out this ratio becomes 3.33, something like this. It has to increase. And if I keep turning up the energy, right, I'll be able to create the tops and the bottoms, and it would alter this as well. Okay. So that's something fun to go look for in experimental data. Do I see these ratios? If the idea, right, that I have fractionally charged objects inside of my protons is right, I should see these relationships in these experimental measurements. Okay. So let's pause on the slides for now. Somehow, how do I stop this? And what I want to do is look at some of the, okay, are you seeing my desktop now?
Yeah.
Okay, so let's take a look at some of the experimental results along these things. So first of all, we talked about jet production, right? So jet production. You guys see the slides, right? I want to make sure.
Yeah.
Okay, great. Right. So here's a picture of some experimental data from CMS. So what is CMS? This is this experiment at CERN where basically they bring two high energy protons in together and collide them with one another. And right, so you can think about it like a big group of fast moving quarks that come in here, and the quarks are going to scatter off of one another and try to escape from that mess. And when they do escape, they should hadronize, right? So this is what they're showing. So we're basically looking at a cross section. So in this picture, the beams would be coming into and out of the page, right? So they're colliding at the center of this detector. And then what do they see? They see that there are a bunch of ordinary hadrons that make their way through the detector, and their energy sort of groups in these interesting areas here. Okay. And so these are the jets. These are the hadrons, but the interesting thing here is that the hadrons aren't symmetrically distributed, right? They get distributed in these chunks. And the interesting thing about that is it's evidence that this hadronization was generated from some small amount, one or two quarks that started this whole hadronization process. And that's why it's chunked up like this, right? If it was just that the hadrons were free to steal the energy, you would expect them to be sort of uniformly just distributed all around the detector. But they're chunked in these certain jet directions, which indicates that they were generated from a few underlying particles in the collection, right? So here there's like 1, 2, 3 primary jets that carry away the momentum. I see some weaker jets here. But these things, if I check, I can find that there's going to be, right, the sum of the momentum. So what would I expect the momentum if I find all my jets? What would the sum of the momentum of all my jets be in this projection?
I imagine 0.
Yeah, should be 0, right? Because my protons are coming, right, transverse to this plane, and so they don't have any initial momentum in this projection that I'm seeing here. And so the sum of the momentum of the jets should also be 0 in this sort of XY plane that we're looking at.
Okay.
And if you click this link, I'll post these slides so you can look at it. You can see a sort of a 3-dimensional image. So here's another picture of the detector, right? So again, so you saw here at the beginning of this video, the protons coming in collide at the center of the detector, create this spray, and you look at all the energy that goes off, and what you find is there's a collection of energy that makes its way through the detector that is very focused in specific directions. And this is a picture of 2 back-to-back jets going off, right? When you just get 2 groups of energy deposited in the detector, that's really interesting because that looks like it must have been generated from a quark and an anti-quark getting pulled apart from some initial interaction that happened inside of these things. And I get them, and look, they go back to back because the total momentum in that projection has to be equal to 0. Okay? So you can see jets. That's already evidence of quarks or some of the properties of the constituent particles that make up the proton. We can make measurements of that R value that we were talking about, right? So here's that ratio of the cross section of E plus E minus creating hadrons to E plus E minus creating muons. And what do we see? So here's this is like think about this like the energy. This is the amount of energy available to us, the center of mass energy along the x-axis. And what you see is that as I turn up the energy, eventually I find, so where's 2? We expected this ratio would be 2. So here's 2. We see that there's a bunch of, right, like when I divide this out, I see that I get these a bunch of points clustering at 2 over a certain energy range. And then look what happens. Eventually I reach a threshold and suddenly that ratio jumps up. Okay. It jumps up to this value of 3.33 that we discussed before, because that's when suddenly I have enough energy available to start making charm. Okay. Sorry, 1 second, guys. Okay, so this is some evidence, right? You can compare these ratios. Now, things aren't perfect, right? I don't see that I'm just at 2 and then I just jump smoothly to, right, 3.33. What I see is that there's kind of weird also blips, right? On average, I'm jumping to these different values, but, right, but I also see like there's a peak here, and then there are these sort of strong peaks here, and then look out here, there's a really big peak that's coming over here. Okay. Well, it turns out this is when I have enough energy to produce a Z boson. So instead of just exchanging a photon, suddenly I have enough energy to do a weak interaction with the E plus E minus, and that changes my cross section in dramatic ways. Okay, and the ratios are different. But at least, right, in these regimes, I can sort of see average behaviors that are strong hints that the quarks actually are fractionally charged objects inside of the proton. They follow these ratios that I can predict from my theory.
So in general, when you get close to the rest energy of a particle, that particle is going to start mucking with this ratio?
Yeah, so these things, right, these other things are, these other little peaks or other resonances that you can have, right? These are specific energies where you're sitting like right at the energy of some bound state particle, and so it preferentially will create those type of particles, and it increases your cross section in an interesting way. So you get these little resonant blips, but the average effect, if you sample over broad enough energy, are these ratios that we discussed here. What else can we do? Well, people can take, and so next lecture, we're going to start talking about the details of QCD and this idea that we have fractionally charged objects that interact with a gluon field. Turns out that we can, right, measure through hadronization, we can find also lots and lots of interesting bound state objects, right? All those little resonances that we saw in there are interesting bound state objects. And so we can go through and try to find, say, the masses of all those interesting little resonances that appear, all those little bound state systems of quarks. And if we have a good theory, we also better be able to predict all of the masses of these little bound state objects that appear here. And this is just kind of a picture. So there's a bunch of, different calculations of different bound state energies that are predicted from theory and the experimental value of that mass that we observe. And so we see that QCD that we're going to describe next time does a pretty good job of predicting the mass of some of these bound state objects like pions, kaons, eta particles. But notice as I get higher and higher in energy, there's some discrepancies. Like here, for instance, all these different theoretical calculations are high for what they're predicting for, say, the delta particle in a systematic way for some reason. And it turns out as I go higher and higher up in energy, that the predictions from QCD become more discrepant with, or at least more varied all over the place from what I see in data. And the general takeaway that we're going to see starting next time is that I can do a lot with QCD in certain energy regions, but there are certain places where QCD becomes really hard to tackle, and there's still a lot of work to understand how to how to get the theory to agree with experiment. What else can I measure? I can measure all these structure functions, right? So here's these F1, F2 structure functions that we talked about before. And if I have enough experimental data, I can start to chunk this into different pieces, right? So here's a function, say an example of experimental data of F2, right? This sort of structure function. So before we had F2 that just depended on Q squared, but I can characterize this in terms of another parameter that I call X. This is a parameter called Bjorken X. It basically tells you about the fraction of momentum that the quark inside of the proton that was struck by the virtual photon was carrying with it. And you can make that an experimental parameter, and it's something it turns out you can measure as well. So basically this tells you how the structure function looks for, right, remember the structure function is this thing that sort of characterizes how the quarks are distributed in the bound state object. But I can also, turns out I have experimental handles, and I don't have time to tell you the details about this, but I have experimental handles to tell you how not only are the quarks distributed, but I can say like the quarks that are carrying, say, a very small amount of the momentum of the system, how are they distributed in the object, right? I can start to divide this up in lots of interesting kinematical ways. And so there's lots of experimental data, and then, right, this is just sitting there begging for some theorist to come and calculate these same things in QCD and see if they agree, right? So this is experimental data. If I have a good theory for QCD, the theory has to agree with this data. Okay. I can also calculate, and we're going to talk more about this again as we go through QCD. I can calculate lots of cross sections, right? I can calculate the cross section for protons to scatter off of one another. How often do, right, what do they break? The total cross section, 2 protons, what's their interaction probability? That should be dominated by QCD because they're objects that contain quarks. I can talk about what's the cross section for them to hadronize into jets or to hadronize into just 2 jets. What's the cross section for me to produce a W from proton-proton, right? So I have proton-proton collision. I can calculate cross sections for them to produce all these interesting objects, right? Again, these are those resonant bumps. How likely am I to produce those resonant bumps? And then if I have QCD, if I have a theory, I can calculate that in theory, and I can compare it to this experimental data. And to date, this is what that looks like worldwide. Okay, this is a fairly recent plot. This is from 2017. The line here, right, this is taking the ratio of the theory compared to data, okay? And then here's these different references. So here, this line is sitting at 1, and you can see the different points here, how well the theory compares to data and the uncertainties on these things. So some of them, notice most of them within uncertainty agree to 1. But there are some places where I'm significantly in disagreement with the theory, right? Like, for instance, this guy here, what is this? If I carry this over, this is W decays into 2 photons. This cross-section is not, right? There's like 2 sigma disagreement between experiment and data. Significant disagreement. Okay. That's hinting at either there's some new physics or there's something, right, we need to calculate the higher order in QCD, or there's something about that process that we're not understanding. Look at this guy. Here's one, again, significant disagreement between the data and the theory. This ratio is quite off. If I trace that back, that's top quark production with a W, 2 tops and a W being produced simultaneously. Something about that is not well understood. So this is interesting, right? Like, at a certain level, we understand things pretty well, but as you make things more and more complicated, as this hadronization becomes more and more complicated, our tools, our theoretical tools, our descriptions of these systems kind of start to fall apart. And we see that as a common trend in QCD. All right, I think we're just out of time, but just to highlight, right? We have lots of these different measurements. We can try to measure as a function of Q squared how the coupling strength between quarks through quantum chromodynamic works. And we're going to get back to this next next lecture, so we'll probably re-show this slide. This is how the charge, essentially the colored charge, is modified. We talked about how that gets modified in the electromagnetic side. There's also an interesting running of this coupling constant for quantum chromodynamics, and it has this interesting shape. And we'll talk about why it has this particular shape where it falls off as I increase Q. And if you're really, I have 2 more slides and then we're done. If you're really, really careful, you can start to ask other interesting questions like, is the proton fundamentally stable, or does it decay with some lifetime, and does QCD predict this? How do the quarks and the gluons carry the spin of the proton? A proton is a spin object, but we know that it's not really just made of these 3 quarks. It's made of this kind of sea of quarks, you know, interacting with one another, exchanging gluons and creating quark-anti-quark pairs. Can we properly calculate how the spin of the proton comes about? Does the neutron carry a neutron EDM? Does it carry an does it carry an electric dipole moment? Okay. The proton spin puzzle is really interesting. It turns out when you do probes of the spin system of the proton, that the ups and the down quarks, right, the quark side of the system, you can start to break this into apart and try to understand, basically, are the quarks carrying all the spin? Is some of it carried by the proton? And to date, there's sort of interesting, right? We don't quite understand how the spin of the proton is generated. If you make a measurement, it doesn't look like all the spin, right? It looks like the quarks and the anti-quarks that are appearing out of the vacuum should sort of give the quark side of this thing the wrong, or not enough spin into the system. And there's all kinds of interesting polarized measurements that are being made at places like Jefferson Lab to try to understand how, in fine detail, using QCD, you generate the proper spin of the of the proton. It seems like just having, you know, 3 spin half objects, I should be able to make a composite object that, you know, describes the spin of the proton. But the details are not that simple because all these gluons are getting in the mix and mucking things up. And the last thing is the neutron spin EDM. Does the neutron have an electric dipole moment? Well, it turns out you can make some experiments to go check for whether or not the neutron has an electric dipole moment, whether or not it likes to have its charges separated onto different sides of the neutron. And that's interesting because if it does, QCD should be able to predict that. And so here what you're seeing on the left is the upper limit of the neutron EDM with time. So you can basically see that that's been getting better and better and better with time. But there are different models that predict under different assumptions about how QCD might work, that the neutron might have a EDM, or if it does have a significant EDM, it's also indication of some new physics that might be sitting there. So people make measurements of the neutron EDM. We haven't observed a neutron EDM to date, so we can at least set limits, and QCD has to predict that the neutron EDM is below a certain amount. So the thing I want to take away here is that we're going to write down QCD next lecture. We're going to start talking about what that theory looks like. But that theory, right, is, I would say, much more theoretical than QED. QED has been measured to incredible levels of precision, and we think it is a beautiful explanation about how charged particles interact. QCD, you see, like, some of the details are still a little bit murky, right? We're going to see at certain energy regimes, at high energies, and in sort of special situations, QCD does a really good job of describing nature, but we don't yet have a handle on QCD at the level where we can just have it describe all of the effects for hadronized objects that we see in nature. And so that's why there's a you know, a huge active community that's still experimenting and making measurements of QCD, you know, quark systems, and we're interested because there's a lot of open questions here. Okay, I kept you guys 5 minutes extra today. I apologize for that. Are there any last questions before we go?
Yes, I have one question.
Yeah, Kinnari, what's up?
Can you just take out the slide of assignment 2?
Can I do what?
The slide of assignment, like you showed all the slides right now. So the slide of assignment.
Yep. This?
Yeah. So this all that this that oral component and the written component. These things are different from what you posted yesterday to the Blackboard, right?
These are different than what I posted to the Blackboard yesterday. Yeah. Yes. Blackboard, the thing I posted yesterday was our final like homework assignment. That was homework 7, right?
Okay.
So this is not the
Okay.
final. It's just the last. I didn't mean, maybe I should change the language. It's not a final. It's the last homework assignment I'm going to give you for the semester. And then we'll have these 2 additional assignments.
Okay, so means this written final student presentation and written report. So means what is the difference between homework 7 and this final?
So homework 7, we posted on Blackboard, right? So we can take a look. Sorry, I closed this. Okay. Yeah, so final, I guess I should have just called this homework 7, so I'll change that. So this thing is not, it's just your last homework assignment, right? So there's 3 problems from Griffiths that you'll find in the thing I posted online.
Okay.
And then I ask you to answer a few questions about the movie that we're going to watch in a
Okay.
pictures.
Okay.
But for the assignment, for the oral and written final, you need to pick a topic that you're interested in and try to describe it.
Okay. Okay.
You know, so for instance, some of these things that I just mentioned on this open questions, like the spin of the proton. What do we know about the spin of the proton? That would be an interesting topic for, you know, for a final presentation. Or, you know, something about weak interaction. How do we understand different processes, you know, interesting things about the weak interaction. If you want to, I can prepare for maybe by next week, I can give a, or I'll try to post up like an example list of topics that you guys might select from for your final presentations.
Okay.
Okay?
Yes, yes. Okay.
Anything else for today?